Hello there and welcome back to the Science Sleepy Minds. Outside your window, the night air hangs still. Maybe there's a low buzz from a street lamp or the faint hum of a refrigerator in the next room. In your hand, a mug that's just a little too warm. You take a sip and it's not bad, but you know, somehow, you'll never get that perfect warmth back. It'll only get colder from here. Everything does. Entropy isn't just a stuffy physics term, it's that creeping sense that things want to fall apart, that messes grow while order shrinks, that socks disappear, ice melts, and you can never quite rewind to the way things were. You've lived it. Now it's time to understand it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me, where are you tuning in from tonight? What time is it there? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're in your kitchen, the tiles cold on your feet. You open the fridge and stare, not sure what you're even looking for. Cold air slinks out, curling around your legs. Inside, everything's been arranged, and then gradually over days, maybe weeks, it's slipped back into mild chaos. Half an avocado, browning. A bottle of soy sauce tipped over. Cheese, maybe. Or was that yogurt? What you're seeing is entropy in action. Every time you open the fridge, a little more heat seeps in. A little more disorder spreads. It's the universe doing what it does best, increasing entropy. Here's the rule, one of the most important in all of science. The second law of thermodynamics says that in a closed system, entropy never decreases. Disorder only grows and energy gets less and less useful. Your fridge is fighting that law every second it's plugged in. It cools its insides by pumping heat out, but it's burning electricity to do it. In fact, that neat little box is producing more entropy outside of it just to keep the inside a little less messy. It's like trying to keep your bedroom spotless by moving all the junk into the hallway. You're not stopping the mess, you're just shifting it. But what is entropy, really? Technically, entropy is a measure of the number of ways a system can be arranged. The more possible arrangements, molecular positions, energy levels, all that jazz, the higher the entropy. Ice has low entropy. Melted water, higher. Water vapor, molecules bouncing around with wild freedom. That's peak chaos. So the more disorder, the more entropy. The more ways something can go wrong, or at least go messy, the more entropy it holds. And the universe? Oh, it loves disorder. It practically breathes it. Well, not breathes, expands it. That's why time only moves one way. That moment when your coffee spills. Entropy just one. You can watch it seep into the carpet, the stain blossoming slowly, but you'll never see it leap back into the cup. In 1850, physicist Rudolf Clausius coined the term entropy from the Greek word tropy, meaning transformation. He was basically trying to explain why steam engines couldn't be perfectly efficient, why some energy always seemed to leak into uselessness. He didn't know he was also describing the death of the universe. Classic 1800s scientist move, just trying to fix a train, accidentally predicts cosmic doom. Historians still argue whether Clausius truly understood the cosmic implications of entropy when he first coined it. Some say he was focused solely on engineering concerns. Others suggest he had inklings of the wider picture. Here's a quirky tidbit. The word entropy wasn't exactly beloved at first. Some early scientists thought it sounded too mysterious, even spooky. One 19th century engineer reportedly called it a foggy, useless concept, which is exactly what someone deep in denial about laundry entropy would say. But the second law stuck around. It started whispering its way into other sciences, chemistry, biology, cosmology, even information theory. The law, simple in principle, brutal in effect. Things fall apart, they don't unfall. Your warm blanket tonight, it's radiating heat away even as you snuggle under it. That ice cream in the freezer, the only thing keeping it from turning into sugary soup is a constant, expensive battle against entropy. And eventually, that freezer will fail, the blanket will cool, the coffee will chill, the stars will fade. Even the sun is playing this game, burning through hydrogen, radiating energy outward, making entropy in bulk. It shines by turning nuclear order into glorious light and irreversible chaos. Now here's where it gets fun. In some fringe interpretations of thermodynamics, entropy isn't just a property of heat. It's the very reason time exists. The past is the low entropy direction. The future is where entropy increases, You age because entropy rises, you forget things, socks vanish, ice melts. That's time, baby. Or at least that's the theory. And just to keep things spicy, there's still no consensus on why the universe started in such a low entropy state in the first place. Seriously, why did everything begin in an improbably tidy configuration? It's like the cosmos was a hotel room right before check-in. Too perfect to be real. Some scientists suggest inflation did it. Others say that it's just a statistical fluke. A few whisper about multiverses, where maybe, somewhere out there, entropy runs backward and coffee unspills. You're still in that kitchen, but now the fridge is humming louder. You can feel the weight of all those systems running in the background. Not just appliances, but physics itself. Keeping things marginally ordered for now, but always, always losing ground. Entropy isn't evil. It's not even tragic. It's just nature doing its thing. And weirdly, it's beautiful in its honesty. Because even in the slide toward disorder, life manages to carve out little temporary oases, a warm blanket, a neatly folded towel, a cat loaf on a windowsill, and you, listening to this, tucked in, brain drifting, are one such pocket of improbable calm in an otherwise chaotic universe. The chaos can wait. The stars above you don't know your name. They burn, churn, and eventually collapse. Not for drama or beauty, but because they have to. Every flicker of starlight is a transaction with entropy. A little more fuel spent, a little more disorder made, and yes, it's stunning, but also doomed. You're lying in bed now, maybe staring up at the ceiling, maybe imagining the cosmos overhead. You picture it how it's shown in movies, galaxies spinning gracefully, comets with dramatic tails, nebulae all glowy and high definition. But if you zoom way out, really out, the universe is mostly just empty. A growing, stretching, cooling void. And that's where we're heading. Not into a bang, not into a scream, just into more nothing, stretched thinner and colder with every second. This is what physicists mean when they talk about the heat death of the universe. Doesn't that sound cheery? Let's unpack it. Slowly, sleepily. The heat death isn't about fire, it's not even hot. It's the ultimate thermodynamic equilibrium, a moment when every bit of energy in the universe has been evenly smeared out, and nothing interesting can happen anymore. No more stars forming, no more stars exploding, no planets warming, no ice melting, just silence. Forever. This is the big punchline of the second law of thermodynamics. Over time, entropy always increases. It's a one-way ride to equilibrium, which ironically is the most boring state of existence possible. No contrasts, no gradients, just lukewarm uniformity, stretched across a very, very tired cosmos. You might be wondering, how does heat cause the universe to die? Great question. It's not that things get hotter and explode, it's that useful energy gets used up. You can't run an engine without a difference in temperature, hot here, cold there. But in a universe where everything is the same temperature, engines stop, movement stops. Even thought, if any minds remain, would be impossible. There's no fuel left, only stillness. The idea first came into focus in the 19th century, when Lord Kelvin started applying the laws of thermodynamics to the entire cosmos. Yes, this is the same Kelvin your freezer setting is named after. While working on heat transfer, he made an unsettling prediction. The universe would eventually run out of available energy. Historians still argue whether Kelvin's version of heat death matches modern cosmology's version, because back then, we didn't know about cosmic expansion or dark energy. But the underlying message remains: the universe is slowly winding down. Fast forward to today. Now we know the universe is expanding, not just slowly but accelerating. Galaxies are racing away from each other faster and faster. Eventually, most of them will disappear beyond the cosmic horizon, never to be seen again. From our point of view, the sky will go dark, and we'll be left with only our own galaxy, and even that will fade in time. One of the last things to go will be the stars themselves. Right now, stars are giant fusion engines. They take hydrogen, simple, light, delicious hydrogen, and smash it together to form helium, releasing light and heat. But eventually, they'll run out of hydrogen. The bigger stars go out with a bang, supernovae so intense they can outshine an entire galaxy for a few days. The smaller ones die more gently, fading into white dwarfs, then black dwarfs, cold, lightless remnants. In the very, very far future, trillions of years from now, The last star will blink out, and then the universe will be lit only by the soft, fading glow of white dwarfs, and maybe a few unlucky red embers. But entropy doesn't stop just because the lights go out. Over quadrillions of years, even the most stable things in the universe begin to erode. Planets spiral into dead stars, black holes evaporate via Hawking radiation, a slow, quantum trickle of particles leaking out of darkness. Yes, black holes, those iconic cosmic vacuum cleaners, actually lose mass over time. Stephen Hawking predicted that they'll eventually vanish, not with a pop, but with a sigh. Here's a fringe tidbit for you. Some physicists once believed black holes were eternal, indestructible, the ultimate storage unit for matter. But in 1974, Hawking's work on quantum mechanics at the Event Horizon showed otherwise. The universe is so relentlessly entropic, even black holes can't survive forever. And so we head toward the heat death, a universe full of extremely low-energy particles, spread across an impossibly vast space, just kind of vibrating mildly. No stars, no planets, no light, no contrast, no potential to do anything, and not even irony. Now you might be tempted to ask, can we stop this? Build a machine to rewind entropy? Physicists get that question a lot, usually right before their third coffee of the day. And the answer is, not really. Entropy isn't just a glitch to be patched, it's the underlying structure of how time and energy behave. It's why things change at all. The kicker? Some theories suggest the heat death isn't just the end of the universe, it's also the beginning. A few bold cosmologists propose that once maximum entropy is reached, the universe might bounce, resetting itself into a new low entropy state, a new Big Bang, a fresh cosmic story. But we're talking about timelines so long, they make dinosaurs look like yesterday's news. It's hard to picture. You'll lose the thread if you try. Better to let it drift like a starless night. So here you are, one tiny creature on one tiny planet, circling one of trillions of stars. All of it temporary, all of it borrowed energy, dancing briefly before the fade. And yet, that's what makes it beautiful. The lights are still on for now. The coffee still warms, the fridge still hums. Entropy might be winning, sure, but it hasn't won yet. You pull the blanket up a little higher. Maybe that's your rebellion. Maybe that's your comfort. The heat death will come. But not tonight. The steam rises from your coffee mug in slow, lazy tendrils. It curls upward, swirls in little spirals, and then vanishes. You give it a gentle stir. The cream tumbles into the darkness, forming ghostly eddies that swirl and stretch and never quite untangle. And that's entropy in action, right there, in your breakfast ritual. See, this simple mug is basically a thermodynamic crime scene. You've taken a relatively ordered system, hot coffee here, cool cream there, and mixed them. Once stirred, the cream doesn't unmix. You'll never see the molecules politely separate themselves again, no matter how long you wait. This irreversible blending, this one-way flow toward uniformity, is how entropy likes to work. It turns distinct things into mush. It smooths out contrasts, and it never puts them back the way it found them. And here's the kicker. The very fact that your coffee was hot is part of the problem. High energy, low entropy. And the moment you exposed it to the world, brought it into contact with cooler air, the energy started bleeding out. Now it's lukewarm. Now it's sad. Now you're drinking mediocrity. Welcome to thermodynamics. This particular law, the second one, gets the most press. But there's a lesser-known cousin in the family, Boltzmann's entropy formula. Engraved on Ludwig Boltzmann's actual tombstone, this elegant little equation links the micro and the macro. It says entropy equals the number of microscopic configurations that correspond to a system's visible state. In other words, your coffee looks like coffee, but inside it's a trillion molecules frantically zipping around, colliding, sharing energy, doing molecular gossip. And there are so many ways those molecules can arrange themselves while still producing something that looks like a mug of Java. Each new arrangement, each random shuffle, increases entropy. That's why when you stir in the cream, you're not breaking anything. You're just allowing more possible arrangements, and the universe loves that. Historians still argue whether Boltzmann truly grasped how revolutionary his ideas were. At the time, atoms were still a controversial concept, and many scientists dismissed his microscopic explanations of entropy. He didn't live to see how right he was. But here's a fun, if grim, fact. Boltzmann's work was so abstract and so poorly received during his lifetime that it reportedly contributed to his depression. Today, we practically worship his insights, but back then, people just wanted their coffee, back to the cream. You might ask, what if I stir really carefully? Can I unmix it? Nice try, but no. Even if you reverse the spoon's motion perfectly, you'd only manage to approximate the original state. At the microscopic level, the molecules have already moved too far. There's no undo button, no Cottrell plus Z for entropy, only forward. This is sometimes called irreversibility, and it's why we know time flows in one direction. Not because clocks say so, but because cream swirls and never unswirls. Because your toast never unburns. Because memories form but don't unform. Even physicists admit, we don't know why the universe started with such low entropy. It's one of the biggest open questions in cosmology. Some say it's pure chance. Others think there's a deeper law we haven't found yet. Maybe even something involving multiple universes. But for now, we work with what we know. Entropy increases. Always. So what does this mean for your daily life? It means your house doesn't get messy out of spite. It's following the rules. Left alone, systems drift toward disorder. Your desk, your closet, your brain when you forget why you walked into the kitchen. Entropy is why you need to clean things at all. Now let's jump from kitchens to something a bit more ancient. Picture the ruins of Pompeii. Streets once full of life, now buried, excavated, decayed. Entropy at work. But the people who lived there, they were creating order, buildings, roads, societies. All these structures were little rebellions against entropy. But rebellions take energy. Human bodies eat calories and convert them into motion, thought, love, construction. Every time you build order, you burn energy and increase entropy elsewhere, usually as heat. Your tidy living room is powered by a messy power grid and a whole lot of waste heat from power plants. So here's a neat paradox. You can locally decrease entropy. Your room can get cleaner, your tea can be reheated, but it always costs energy and produces even more disorder somewhere else in the system. The universe always balances the books, which brings us back to that cup in your hands. As the coffee cools, it shares its heat with the surrounding air. The molecules slow down. The whole system, coffee plus room, creeps toward equilibrium, where everything is the same temperature. No more heat flow, no more contrast, just meh. And once that happens, no more work can be done. A steam engine can't run if there's no difference in heat. A planet can't host life if its energy is flat. Contrast is life. Entropy is the slow smoothing of that contrast. And eventually all the cream's mixed, all the heat's shared, all the contrast is gone. But before you go full nihilist, let's toss in a quirky tidbit. There's actually an ice cream flavour called Entropy. It's a chaotic swirl of multiple other flavours, designed to look like a messy collision in a bowl. Not endorsed by physicists, but highly approved by snack enthusiasts. In the end, the story of entropy isn't about destruction, it's about transformation. Things don't vanish, they just become less useful. High-quality energy becomes low-quality heat. Order becomes chaos, hot coffee becomes disappointment. But also, clouds become rain, rain becomes rivers, rivers carve canyons. Even entropy has a kind of grace. So tomorrow morning, when you pour cream into your mug and give it a stir, take a moment. Watch the swirl. That's time, right there. That's the second law of thermodynamics writing its poetry. One curl of white in the dark, then another, until everything blends. Unrepeatable, unreversible, beautiful, and then drink it before it gets cold. You step on a Lego in the dark and immediately wonder if time can be reversed. If just this once, the universe might give you a do-over. Spoiler, it won't. Time, like spilled milk and most of your online purchases, only moves one way, and it's entropy's fault. Right now, you think of time as seconds ticking by on a clock. Neat, predictable, linear. But clocks are just tools. Time isn't made of gears or digital screens. It's made of change, and the most reliable kind of change we know, entropy increasing. That's the true heartbeat of time. So why does time move forward? Why can't we undrop the glass, or rebake the cake, or return to last Tuesday when your charger still worked? Here's the answer that makes physicists sigh and philosophers lean forward in their chairs. Time's arrow points in the direction of increasing entropy. That's it. That's the rule. You experience time because things change in ways that can't be undone. Cream doesn't unmix, houses don't uncollapse, the cat does not unvomit on the carpet. Ever. And yet, the microscopic laws of physics, the ones that govern atoms and particles, don't actually care about direction. In theory, you could reverse every motion at that level and the universe would look fine playing backward. A bouncing ball would bounce just the same. Colliding particles would scatter, then rejoin perfectly. But in the real world, that never happens. Not because it's impossible, but because it's wildly improbable. Rewind every molecule in a cup of coffee exactly and sure, the cream might unmix. But the chances of that happening on its own are about the same as your phone charging itself from 0 to 100% by lying in the freezer. Possible? Technically. Likely? Number? Like, really no. This is where we meet Ludwig Boltzmann again. He proposed that the arrow of time comes from probability. Low entropy states, like a neat bedroom or an unshattered egg, are rare. High entropy states are common. There are just so many more ways for things to be messy than for them to be tidy. Historians still argue whether Boltzmann's statistical approach to time was too philosophical for his peers or too ahead of his era. Either way, his idea stuck. Time is entropy's shadow. Now let's get weird for a second. There's a fringe idea known as the Loschmidt paradox, which asks, if physics is time-symmetric, why don't we see things unhappen? It's a fair question. If we can model a collision going both forward and backward, why does reality only do the forward version? One popular answer, initial conditions. The universe began in an extremely low entropy state, a kind of cosmic neat freak moment. From that highly ordered Big Bang, entropy's only had one direction to go, up. The mess is spreading outward from that moment and we're caught in the flow. It's like starting with a freshly shuffled deck and watching it scatter across a windy beach. You'll never get that order back. So your brain processes time because events are unfolding into disorder. You remember the past because it was tidier. The future is fuzzy because entropy hasn't scrambled it yet. Your memories are snapshots of lower entropy moments stored in a biological hard drive that's constantly losing clarity. Ever notice how nostalgia always feels warm and clear, but the future feels full of static? That's not just emotion. That's thermodynamics. Now take a breath. We're still floating in this quiet moment together. You're warm. The room is still. And yet even now, time is moving. Not because the clock says so, but because heat is leaking from your body into the air. Electrons are jumping around in your devices. The molecules in your pillow are vibrating just a little less energetically than they were 5 minutes ago. You are aging, but gently. Let's roll with an analogy. Imagine a sandcastle on a beach. It takes time and effort to build. Smooth towers, sharp edges, maybe even a little seashell moat. That's a low entropy structure. But leave it alone. Waves hit, wind blows, people walk by. Eventually it's just sand again. High entropy. No one has ever seen sand randomly assemble into a perfect sandcastle. Doesn't mean the laws of physics say it can't happen. It's just so unlikely that it might as well be forbidden. And yet, this is the kind of magic we perform every day. You make dinner, you write emails, you make your bed, you bring order to small corners of the world again and again against the current. But it always costs energy. Calories, effort, time. You're a local reversal machine, briefly holding back entropy with willpower and caffeine. Let's go even deeper. Einstein's theory of relativity treats time as a dimension, one you move through like space. Technically, there's no now that's the same for everyone. If you zip around near the speed of light, your time slows down compared to someone sitting still. GPS satellites actually have to correct for this. Time is not universal, but entropy always knows which way is forward. Always. Wherever you go, whatever speed you travel, disorder increases. In that way, entropy is more honest than time. And here's a little fringe tidbit for your dreams tonight. Some physicists have played with the idea of two universes, mirror reflections of each other, where entropy increases in opposite directions. In one, time flows like ours. In the other, it flows backward. The past is their future. The future, their past. If they exist, they'd never know about us, and we'd never know about them. Wild, huh? But for you, here in your bed, everything is still flowing forward. Your memories pile up. Your blanket cools. The sounds in your home slowly shift towards silence. And entropy carries time with it. one quiet second at a time. Tomorrow the coffee will swirl again, and you'll stir it knowing that this moment, this exact blend of atoms and warmth and light, will never happen again. It will only change, never reverse. But that's not a tragedy. That's what gives life its flavour, its sweetness, its spark. That's why you remember the good moments, because they don't loop. They pass, and then they're gone. Just like time, you're in a softly lit room, maybe half listening now, your body slowly untangling itself from the day. But somewhere in the back of your mind, a question still flickers. Half dream, half science quiz. Can entropy be cheated? Is there some clever little loophole hiding in the fine print of the universe's rulebook? Enter Maxwell's demon. No, not a real demon, though it does sound like a character from a steampunk novel who plays chess in abandoned clock towers. This particular demon lives only in thought experiments, conjured up by physicist James Clerk Maxwell in the 1860s, the same guy who gave us the equations behind electromagnetism and probably never lost a staring contest with a chalkboard. So here's the setup. Imagine a box of gas divided into two halves by a wall with a tiny door. The molecules on both sides are bouncing around like toddlers on espresso. Now introduce the demon, a tiny tireless being who watches the molecules and only opens the door when a fast molecule comes from the left or a slow one from the right. Over time, the right side fills with fast, hot particles. The left side fills with slow, cold ones. Suddenly you've got a temperature difference. Without using any energy, the demon has created order out of chaos, reduced entropy, magic. Or is it? For decades, Maxwell's demon haunted physics. It shouldn't work. It violates the second law of thermodynamics. But it's just a thought experiment, right? So why did it bother scientists so much? Because it poked right at the foundation. If this little guy could reverse entropy, even just a little, maybe the second law wasn't as ironclad as we thought. Maybe time could be undone. Maybe your cold coffee could unmix. Maybe the cat could re-vomit in reverse. Still gross, but efficient. Historians still argue whether Maxwell intended his demon as a serious challenge to entropy, or just a playful nudge to his peers. Either way, it worked. The demon became a scientific meme centuries before Twitter ruined everything. So what finally shut the demon down? Turns out it's not the sorting that's the problem. It's the information. In order to observe the molecules, make decisions, and open or close the door, the demon has to store and process data. And data has entropy too. In the 20th century, physicist Leo Szilard and later Rolf Landauer helped us understand that information isn't free. Recording, storing, and especially erasing information increases entropy. The act of choosing which molecule to let through the door actually burns energy, just very quietly. So the demon doesn't break the second law after all. It just hides the mess in its memory. Cheaters never prosper, especially not thermodynamic ones. But the demon lives on as a reminder that entropy is tangled up with more than just heat. It's connected to information, probability, choices. Every system that stores or transfers data is dealing in entropy. Your brain? A warm, squishy entropy engine. Your phone? Same thing, just shinier. Even writing a to-do list is an act of temporary order, a small resistance against the tide, and when you crumple it up and toss it, you're increasing entropy in 3 different dimensions: mental, physical, and emotional. Here's a quirky tidbit. In recent years, scientists have actually built physical systems that mimic Maxwell's demon. Tiny nanoscale devices that sort particles or information in very precise ways. But guess what? The entropy cost still shows up. Always. Somewhere in the background, energy gets spent, heat gets released, and the universe balances the books. So no, you can't beat entropy, but you can game it for a little while. Like when your fridge cools your food. It's not reversing entropy. It's just using energy from the wall outlet to move heat out of one place and into another. A highly orchestrated shuffle of molecules paid for with fossil fuels and a slightly terrifying electricity bill. Or when you clean your room, you're not undoing disorder, you're exporting it. Trash to the bin, dust to the air, calories burned, frustration increased. You can locally reduce entropy, but the cost is global. And this brings us to the heart of the issue. Every system that appears ordered is leaking entropy somewhere else. Life, as we know it, is only possible because the Earth constantly receives energy from the sun. Plants turn sunlight into sugar, animals eat plants, we eat everything. It's a glorious pyramid scheme of energy conversion. But the sun? It's just a giant entropy factory, fusing hydrogen, radiating heat, slowly dying. It's giving us order at the cost of its own. And when the sun is gone, no more cheat codes. That's the delicate dance. We live in an entropy economy. Everything comes at a cost. Every structure, every idea, every moment of clarity. It's all borrowed time. And someone, or something, always pays, even that imaginary demon. You stretch a little, maybe sigh. Your body too is in the game. Cells constantly working to maintain order, pump ions, repair damage, write proteins. Every heartbeat, every breath is a small push against entropy. Not forever, just for now. Eventually, entropy will win. That's not morbid. That's the deal. But in the meantime, we get to do things like listen to sleepy science stories, sip tea, rearrange furniture, and wonder whether we could have outwitted a thought experiment from 1867. So tonight, as you drift, think of that tiny demon, crouched in its box, squinting at particles, trying so hard to cheat the system. It never really had a chance. But you've got something it never did. A warm blanket, a quiet room, and the knowledge that order, however fleeting, is still worth creating. Somewhere in the dark, a star is being born. It doesn't roar into existence with fireworks or fanfare. It begins as dust, a cloud, impossibly vast, spread across light years, cold, sparse, barely there. And yet, over time, millions of years give or take, gravity gets to work. Molecules pull toward each other inch by inch, bump by improbable bump, and the cloud begins to collapse. You might not think of entropy when you picture a newborn star. It feels like the opposite of chaos, right? Something orderly forming out of cosmic fog, a bright ball of heat and light rising from the ashes of a cold, dusty nothing. But here's the kicker. Even starbirth is a victory for entropy. Wait, what? Let's slow that down. In the early universe, things were surprisingly smooth. After the Big Bang, matter and energy were spread out fairly evenly, just the tiniest ripples in the cosmic soup. Low entropy. There were no stars, no galaxies, just a thin, hot fog cooling over time. And yet, that uniformity, that was order. And the collapse into stars and galaxies, that was disorder increasing. Sounds backward, right? You'd think that a cloud collapsing into a focused, structured object would reduce entropy. But gravity's a tricky beast. You see, in gravitational systems, clumping equals higher entropy. That's because there are more possible ways for a bunch of particles to exist when they're not evenly spread out. When matter starts to clump, energy gets released, like heat during the collapse. That energy escapes, allowing the particles to sink deeper into the gravitational well, and that sinking, chaotic, energetic, irreversible, is exactly what entropy loves. Historians still argue whether early cosmologists fully appreciated the weird relationship between gravity and entropy. Some thought of star formation as anti-entropic, a rare oasis of order. But modern astrophysics tells a stranger story. Even the birth of stars is a march toward greater disorder. So there you are, lying in bed, drifting, and above you, far above, entire clouds of hydrogen are collapsing under their own weight, heating up, spinning, condensing into fusion-powered beacons. The star you see now, our Sun, was once one such cloud. Around 4.6 billion years ago, in a corner of what would become the Milky Way, a pocket of interstellar gas gave into its own gravity. As it collapsed, the center grew hotter, denser, until finally hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. And that fusion? That's entropy's masterstroke. Because fusion turns low entropy particles, simple hydrogen atoms, into higher entropy states. It releases photons, neutrinos, and heat. The reactions at the core of a star are so fierce, so relentless, that they pour out millions of tons of energy per second. Every beam of sunlight that touches your skin, warms your tea, grows your plants, that's entropy doing its thing. High-quality fuel being turned into radiant chaos. It's a beautiful paradox. Stars are temporary engines of order, fueled by disorder, and they don't last. Eventually the hydrogen runs out, fusion slows, the core contracts. For massive stars, things get wild. Helium starts fusing, then carbon, then heavier and heavier elements, all the way up to iron. And iron, that's the end of the road. You can't get useful energy from fusing iron, so the party ends. What happens next depends on the size of the star. Some go quietly, shedding layers into glowing clouds and leaving behind a white dwarf, a hot, slowly cooling ember. Others die spectacularly, collapsing inward and then exploding outward in a supernova, flinging enriched matter across the galaxy. That explosion is entropy on steroids, a chaotic release of energy, motion, and matter that literally seeds the universe with the elements needed for life. Iron in your blood, calcium in your bones, gold in your earrings, all forged in ancient stellar deaths. Stars die so that atoms can live. Here's a fringe tidbit for your stargazing thoughts. There are rogue stars, entire suns, ejected from their galaxies by gravitational slingshots. Some travel alone for billions of years through intergalactic space, burning quietly with no planets, no moons, no audience. Just entropy, humming in the background. Even lonely light adds to the mess. Because light, once released, never comes back. It spreads, thins, stretches with the expanding universe. A photon from a star born before dinosaurs may still be flying through space right now. Cooler, redder, less useful. That's redshift, and it's entropy's way of dragging even light toward uselessness. You might wonder, if everything's increasing in entropy, why do stars seem so organized? Because they're temporary, fleeting. Order can exist for a moment, as long as it's paid for with disorder elsewhere. Stars burn because they can, but they pay for their glow with every tick of the second law. They are entropy's brightest sparks, and you, curled up in your blanket, are part of that same cycle. Every breath you take burns energy. Every thought, every memory, every dream costs something. Not in guilt or taxes, but in physics. Your cells maintain their function by consuming fuel and creating waste, heat, carbon dioxide, disorder. You are, in a way, a tiny, delicate star, burning slowly, shining briefly, fighting entropy by becoming part of it. And that's okay. The stars above are not eternal. They never were. They are born of collapsing clouds, grow bright with fusion, and then fade or explode. Their lives are short compared to the universe, and yet without them there'd be no planets, no chemistry, no you. So next time you look up at the night sky, remember, each pinprick of light is a temporary flame, burning for a moment in the cold, dark stretch of forever. And behind that beauty, entropy, patiently turning every bright thing into ash. It's not tragic. It's just the way things go. The air out here is quiet, still, vast. You drift toward the edge of nothing, watching the stars fade behind you, and then suddenly, gravity tugs. Light bends. Space itself seems to fold. You've arrived at the mouth of a black hole. Now, if entropy were a collector of all things messy, all things scattered, all things that fall apart, then black holes are its most dedicated hoarders. They're not just dense, they're obsessed. They eat light, they eat matter, and strangest of all, they eat entropy. You'd think these ultra-compact cosmic monsters would be the most ordered things in the universe. Just a single point, known as a singularity, sitting behind a perfectly round event horizon. No spinning atoms, no moving particles, just pure gravitational collapse, very tidy, very final. And yet black holes have enormous entropy, like mind-bendingly enormous. It was Jacob Bekenstein in the 1970s who first proposed that black holes actually must have entropy. Why? Because if you throw a high entropy object, a messy, hot, chaotic thing, into a black hole, that disorder can't just vanish. The second law still applies. So the black hole itself must somehow account for the lost entropy, or physics throws a tantrum. Historians still argue whether Bekenstein's early equations were radical genius or pure guesswork. Either way, they changed everything. Then came Stephen Hawking, who took things even further. Using quantum theory, he showed that black holes aren't eternal. They actually emit radiation, now called Hawking radiation, and over unthinkably long spans of time they can evaporate. Let's pause on that. The most terrifying objects in the universe, things so dense that not even light can escape, are actually leaking. Not fast. You don't need to worry about the Milky Way's central black hole turning into a puff of gas while you're brushing your teeth. But over quintillions of years they radiate away, and in doing so, they slowly, gently, release their colossal stores of entropy back into the universe. It's the ultimate long game, but even black holes can't cheat the second law. Here's the truly weird part. The entropy of a black hole isn't related to its volume, but its surface area, specifically the area of its event horizon. That's the invisible boundary around it, the place where, if you cross it, you're not coming back. And the bigger the surface area, the more entropy the black hole holds. Let's say that again, because it's bizarre. Entropy in black holes scales with surface area, not volume. That's like measuring how messy your closet is based on how big the door is, not what's inside. This realization led to the birth of something called the holographic principle, a radical idea suggesting that all the information in a volume of space can actually be described by the information on its surface. In other words, the universe might be a kind of hologram. Fringe, yes, but some very serious physicists take it very seriously. Now let's get even stranger. Black holes, by their nature, destroy information. Or so we thought. If you toss a book into a fire, sure, it's unreadable, but the information is technically still present in the ash and smoke and heat. But if you toss that same book into a black hole, where does the information go? This is known as the black hole information paradox, and it has haunted physicists for decades. If black holes evaporate, and the particles they release are random, then the information they contain is lost forever. But quantum mechanics says that information can't be destroyed. So, who's lying? Thermodynamics, quantum theory, gravity. This paradox launched entire fields of research. Some scientists think information gets encoded in the Hawking radiation in ways we don't yet understand. Others believe it's stored in a kind of holographic skin around the event horizon. And a few suggest it never truly enters the black hole at all, it just kind of appears to. Even today, the debate rages. Historians will probably still be arguing about it in 1,000 years, assuming the historians themselves haven't been consumed by black holes, which seems a bit dramatic, but you never know. Here's a quirky tidbit. Stephen Hawking once made a bet with another physicist, Kip Thorne, about whether information could escape a black hole. For years, he stuck to the idea that it couldn't. But in 2004, he publicly admitted he was wrong. He even gave Thorne a signed copy of a baseball encyclopedia, because apparently even black hole arguments deserve a sense of humour. So let's bring this back to entropy. Black holes are the universe's ultimate entropy sinks. Every time something falls in, a planet, a star, an overly enthusiastic spaceship, all the disorder it carries gets added to the black hole's tally. The event horizon grows, the entropy increases, always, but nothing lasts forever, not even singularities. In the unimaginably distant future, after all stars have died, after galaxies have drifted apart, black holes will be the last things left. Quiet, cold, slow-burning shadows in a darkening sky, and one by one, they'll shrink, fade, evaporate, releasing their entropy back into the universe. And then, nothing. Not a poetic nothing. Just nothing. The black holes will be gone, the matter will be gone, even light will be stretched so thin it barely counts. The universe will be, quite literally, spent. All entropy, no structure. But for now, you're here. You, in your bed, still warm, still breathing, still thinking about giant invisible spheres of doom that somehow obey quantum laws and hold the secrets of the universe's memory. Casual. The black holes are far away, quiet, patient. They're not coming for you. Yet. So pull the covers up. Close your eyes if you haven't already. Let the distant hum of entropy swirl through your thoughts, as even the darkest parts of the universe play by the same quiet rule. Everything falls apart, even the things that swallow everything else. The universe is still expanding. Quietly, steadily. Like a balloon you forgot you were blowing up until it's just there, stretching into every direction with no edge in sight. And as it grows, something strange happens to the light inside it. It fades, it cools, it forgets where it came from. This is the story of starlight, and how even the most radiant, life-giving energy ends up cold and tired in the end. Let's rewind for a moment. Right after the Big Bang, the universe was a seething hot plasma, so dense and opaque that light couldn't travel far without smashing into something. But after about 380,000 years, give or take a few yawns, it cooled enough for atoms to form. Suddenly the universe became transparent. Light could finally move freely. That ancient glow still exists today as the cosmic microwave background, or CMB. It's the oldest light we can see, but here's the thing, it didn't stay warm. As the universe expanded, those photons got stretched. What started as high energy, visible or infrared light has now been redshifted into long, cold microwaves, only a few degrees above absolute zero. That's stretching. That's entropy again. The energy isn't gone. It's just been spread out, diluted across space, thinner, weaker, less useful, like hot soup left on a cold counter for 14 billion years. So what happens to the light from stars? The light you see when you look up at night? The answer is the same. It fades. Not because it's blocked or absorbed, but because the universe is expanding faster than the light can keep up. Right now, light from most galaxies is still reaching us. You see their ancient glow in telescopes, or maybe in your phone's lock screen if you're into astronomy wallpapers. But the universe's expansion is accelerating thanks to something mysterious and deeply chill-inducing called dark energy. Over time, galaxies will drift farther and farther apart. Eventually, most of them will disappear beyond the cosmic horizon, a boundary beyond which light will never, ever reach us, no matter how patient we are. It's not that the galaxies vanish. It's that space stretches so fast between us and them that their light never makes it to our corner. Imagine waving goodbye to a friend, and even though they keep waving, the light from their hand stretches out until it's too red, too cold, too faint to ever reach your eyes. That's the future of starlight. One by one, the lights wink out. Not because the stars have died, but because the space between us has become too vast to bridge. Historians still argue whether early 20th century astronomers like Edwin Hubble realized just how permanent this expansion would be. Some thought it might slow, or even reverse. But now, most data points to an infinite stretch, no big crunch, just a long, slow drift toward loneliness. Now for a fringe tidbit. Some physicists believe the universe's expansion might one day become so intense that it rips apart galaxies, solar systems, even atoms. They call it the Big Rip. Not the most relaxing bedtime thought, but don't worry, it's purely theoretical and scheduled for way after your next few trillion naps. Still, even without a rip, the outcome is the same. The stars burn out. Their light gets redshifted beyond visibility. The photons continue to travel, but they get stretched into such long wavelengths that they can no longer interact with anything in a meaningful way. And when energy can't do work anymore, it becomes part of the universal entropy pile. Another drop in the great soup of unusable energy. Take our sun, for example. It pours out energy in every direction. Some of that energy hits the earth, powers plants, warms oceans, charges your phone, toasts your bread, useful stuff. But most of that light just flies off into space, and once it's out there, it's gone for good. Cold, disconnected, forever falling into the abyss. Multiply that by every star in every galaxy, every photon cast into space, drifting, stretching, fading. The sky isn't filling with light, it's leaking it. And here's the ironic twist. Entropy is both responsible for the light's journey and its eventual silence. Without entropy, there would be no thermonuclear fusion, no starlight at all. But entropy doesn't know how to stop, it doesn't settle, it stretches, it spreads, it forgets. And so the light becomes background, first dimension, then invisible, then irrelevant. You, lying here now, are experiencing a kind of temporary miracle. Your eyes, your senses, your very metabolism, they all depend on the heat and light of nearby stars, on contrast, on gradients, on difference. This isn't the default state of the universe, this is the brief. Later, much later, there will be no such difference. No warm stars, no cool planets, no useful photons, just a dark sea of red-shifted relics, still moving but no longer glowing. This is the path toward thermal equilibrium, the dreaded state where everything's the same temperature, where no work can be done, where every last spark has been traded for entropy. But we're not there yet. You can still feel warmth, see light, watch shadows shift on your ceiling. You live in the thin middle layer between the low entropy birth of stars and the high entropy death of light. A momentary ripple, a pocket of possibility. And maybe that's what makes starlight so beautiful. It's not permanent, it's not even stable. It's a one-way gift, doomed to fade, and precisely because of that, it's meaningful. So tomorrow, if you catch a glimpse of the stars, or even just the golden edge of sunrise peeking through your curtains, remember, it's not just light, it's entropy in its most generous phase. One day it'll all stretch into silence, but tonight, the light still travels, and you're still here to catch it. Your body is not quiet. It hums, constantly. Beneath the stillness of your limbs, inside the hush of your breath, trillions of cells are working overtime, burning energy, repairing tissue, responding to microscopic messages, fighting off invaders, all to keep you in one improbable peace. You may be lying still, but make no mistake, your body is waging a slow, valiant war against entropy. And like all wars against entropy, it loses, eventually. Life is the ultimate temporary arrangement, beautiful, complex, structured. But all that structure comes at a cost. You are a machine that runs on borrowed order. Let's break it down gently. Every second, your cells are converting energy, usually in the form of glucose and oxygen, into usable work. This happens mostly in your mitochondria, those tiny little bean-shaped powerhouses that your 7th grade science textbook was way too excited about. Inside, chemical energy is turned into ATP, the cell's currency, and spent on processes like moving ions, contracting muscles, or sending nerve signals. But no conversion is perfect. Some energy is lost, as heat, as waste, as entropy. Your body is, at its core, a controlled burn. You take in food, low-entropy, energy-rich molecules, and you exhale carbon dioxide, heat, and water, high-entropy leftovers. Your body is like a very polite bonfire, quietly reducing structured fuel into atmospheric debris. And the result? You stay alive. For a while, aging, as it turns out, is entropy catching up with you. It's not just wrinkles and grey hairs and losing track of your keys more often than you'd like. It's the slow accumulation of molecular damage. Tiny bits of cellular mischief, DNA mutations, proteins folding the wrong way, junk accumulating in your cells like digital clutter in an old hard drive. Your cells do their best. They clean up, they repair, they recycle, but over time the damage outpaces the repair. Systems get overwhelmed, the mess spreads. Historians still debate when the idea of aging as entropy first took hold. Some point to early 20th century studies in thermodynamics and biology, others to mid-century genetic research. What's clear is that entropy offers a painfully elegant explanation. Life is a constant, temporary reversal of disorder, and aging is the gradual surrender. Even your brain, the soft gelatinous engine behind your dreams, isn't immune. Neural pathways degrade, signals slow, information storage becomes noisy. That name you couldn't remember last week? Blame a little spike in cognitive entropy. But don't panic, because here's the beautiful bit. Entropy may be inevitable, but life still finds loopholes. For billions of years, organisms have evolved elaborate strategies to survive, at least for a while, by outsourcing entropy. Plants, for example, perform photosynthesis. They take in sunlight, pure energy, carbon dioxide, low energy, and water, and turn it into sugar, useful, organized energy. But they do this by increasing entropy elsewhere, releasing oxygen, warming the air, stirring the ecosystem pot. Animals like you and me just borrow that work. We eat the plants, or the things that ate the plants, digest the sugar, burn it, and create even more entropy. And yet, in that process, we grow, think, love, dance badly at weddings, and it's all worth it. There's a quirky little fact you might enjoy. Humans are not thermodynamically efficient. At rest, we convert only about 25% of our energy into mechanical work. The rest, lost as heat. Which is why you're always warm under the covers, even when the room's chilly. Your metabolism is just very inefficient and very cozy. That inefficiency, it's entropy in disguise. In fact, warmth is a direct byproduct of entropy. Every breath you exhale is slightly warmer than the air you took in. Every heartbeat, every muscle twitch, every midnight toss and turn under the blanket, all of it radiates heat into the world. You are an entropy machine with feelings, but don't feel used, because in that mess, in that heat, in that irreversibility, comes the magic of being alive. Let's look deeper. Your DNA, the spiral staircase that encodes you, is subject to entropy too. It's constantly being copied, repaired, and occasionally messed with. Errors happen. Most are harmless. Some are useful. Hello, evolution. Others? Not so much. Cancer, for instance, can be viewed as a localized entropy event. Cells ignoring the tidy rules of division and order, choosing chaos. And again, your immune system responds. It uses even more energy, more heat, more entropy. The battle never stops. Even death, the thing we all quietly sidestep in conversation, isn't the end of entropy. It's just the moment your body stops maintaining order. The cleanup crew packs up, the structure unravels, molecules drift, bacteria join the party. But in nature's ultimate recycling program, that disorder gets passed on. Your atoms become part of something else. Grass, soil, air, stars eventually. You never disappear, you just get redistributed. Entropy isn't the villain. It's the reason life had to evolve in the first place. Think about it. If the universe were perfectly still, perfectly uniform, with no gradients, no differences, nothing could ever change. No life, no death, no Wi-Fi. Entropy makes things happen. It gives life something to push against. And yes, it always wins. But it lets you play first. So here you are, lying in bed, muscles relaxed, temperature dropping slightly as you drift towards sleep. Your body still working, still burning a little glucose to keep you going, still fighting, gently, against the dark. You are a marvel of temporary order, a candle flickering against the wind. You won't last forever. But then again, neither will the wind. Your room is probably calm right now, blanket tucked just right, the air gently stirred by a ceiling fan or that oddly comforting hum from a nearby appliance. You've made your little island of order for the night, and that's beautiful. But step outside that bubble, figuratively of course, and you'll find that entropy isn't just personal, it's everywhere. Cities, societies, civilization itself. Yes, even empires crumble because of entropy. Not immediately, not in dramatic Hollywood fashion, but slowly, inevitably. One spreadsheet error, one rusting bridge, one corrupted backup file at a time. Let's start close to home, your storage closet. You know the one. You organized it once, bought labeled bins, made a whole Pinterest board about it, and for a while, it was perfect. But now, it's chaos. A tangled mess of cords, expired batteries, a single rollerblade probably. And no matter how often you tidy it, entropy creeps back in like a raccoon through a doggy door. Civilizations do the same thing, just on a much, much larger scale. They start with grand visions, laws, systems, roads, markets article, 1,000 structures, both literal and metaphorical, to hold back the tide of disorder. And it works, for a while. Rome built aqueducts, China wove silk across continents, the Maya tracked the stars. But all these civilizations face the same quiet enemy: energy loss, complexity fatigue, and organizational decay. As societies grow, they consume more energy, not just food or fuel, but administrative energy. That's right. Even keeping track of the rules costs energy. Bureaucracies swell, communication slows, infrastructure ages, maintenance is deferred, and entropy creeps in. There's a concept in systems theory called maximum entropy production, the idea that systems evolve to produce entropy as efficiently as possible. Some scientists suggest that civilizations themselves may be entropy machines, gathering energy from the environment and transforming it into complex structures that eventually break down. Historians still debate whether entropy can be directly applied to social collapse, whether it's fair to say a failing empire is just a thermodynamic inevitability. But even as metaphor, it's eerily compelling. Consider the Roman Empire. It was a marvel of engineering, law, and military might. But by the end, it had overextended itself. Roads and aqueducts crumbled, corruption spread, the economy destabilized. Eventually, the energy required to maintain the empire exceeded what it could extract from its provinces. The balance tipped. Disorder won. Sound familiar? Today, modern civilizations wrestle with entropy in digital form. Data centers hum day and night, cooling their processors and archiving billions of emails no one will ever read. But information decays too. Hard drives fail. Code becomes obsolete. And backups. They always corrupt just when you need them. There's even a specific term for entropy in data systems, bit rot. Left unchecked, stored data can slowly become unreadable, like ink fading from an old scroll, just quietly vanishing. We live in the most information-dense era in human history, and yet it's all balanced on a digital knife's edge. Without energy, without maintenance, without constant vigilance, our knowledge would fade faster than a chalk drawing in the rain. Here's a quirky tidbit. The US government once stored important records on microfiche, thinking it was a stable format. Turns out some of those films degraded faster than expected, thanks to humidity, Poor storage or just bad luck. Entire archives quietly dissolved. Entropy doesn't need drama. It prefers slow leaks. Even language follows the trend. Languages evolve, diverge, simplify, or complicate depending on who you ask. Rules get bent. Words get borrowed. Over generations, entire grammars drift into something new. The tidy Latin of Caesar becomes the relaxed French of today, a kind of linguistic entropy. Order to variation to delightful confusion. Architecture follows suit. Cities sprawl, then rot. Buildings erode. Paint fades. Bridges rust. Every man-made object slowly yields to the elements. Gravity, oxidation, moisture, mold. We fight it with steel and sealant and quarterly maintenance budgets. But the moment we stop, nature resumes the teardown. And yet, somehow, we keep building. Why? Because temporary order still matters. Entropy doesn't mean don't bother. It means appreciate the temporary. The sidewalk won't last forever, but it lasts long enough for someone to walk home. The library might crumble in 1,000 years, but right now someone inside is learning something new. Every act of civilization is a rebellion against entropy, and also a part of it. Take power grids, for example. They exist to deliver usable energy across vast distances, but the longer the wires, the more energy is lost as heat. That loss, pure entropy. Even the most high-tech systems bleed order into chaos. Same with transportation. Planes, trains, and automobiles. They move us, feed our economies, connect our lives. But they also burn fuel, emit waste, wear down. Engines turn organized fuel into disorganized exhaust. Roads crack, tires wear. Entropy never misses a ride. So what's the point? Why build anything if it's just going to fall apart? Because the fall is part of the beauty. We build not for permanence, but for meaning, for connection, for a sense that, even briefly, we shape the world into something that made sense. And if entropy is the cost for all of that, so be it. So tonight, in your quiet room, surrounded by all the little pieces of your personal civilization, phone charging, lights dimmed, socks somewhere on the floor, just remember, you're both a builder and a witness. You create tiny pockets of order, and you watch them slowly return to the cosmic junk drawer. And that's okay. The fridge hums, the router blinks, your digital empire holds for now. Let it be enough. Your fridge is lying to you. It hums with calm authority like it's in control. The door swings open, revealing its cold, glowing shelves. Your yogurt, your leftovers, maybe one lonely pickle that nobody wants to admit is still in there. It looks so neat, so under control. But the truth is, your fridge is an entropy factory, just like your car, your air conditioner, your phone, your favourite scented candle even. All of them are machines trying to create a little pocket of order at a cost. Let's start with the fridge, since it's quietly judging us right now. It appears to reduce entropy by keeping things cold, slowing down the chaos of bacteria and spoilage. You open the door, and it feels like order lives inside. But in truth, that low entropy inside your fridge is being purchased by pumping heat into the kitchen. Your fridge works by taking thermal energy from inside its box and moving it outside, where it disperses into the air. And to do that, it uses a compressor, a coolant, a bunch of coiled pipes, and electricity. And that electricity? It's generated by burning fuel somewhere, somehow, releasing even more entropy into the world. You've just outsourced the mess. This is true for all heat engines, cars, jet turbines, lawnmowers, even steam-powered Victorian dreams. They convert energy from one form to another, usually from chemical or thermal into mechanical work. But none of them are perfectly efficient. They can't be, because of the second law of thermodynamics. That's where Carnot's theorem comes in. In the 19th century, French engineer Sadi Carnot worked out the theoretical limits of efficiency for heat engines. He proved that no engine can be 100% efficient unless it operates at absolute zero, which for the record is impossible. Sorry, sci-fi fans. Historians still argue whether Carnot truly foresaw how foundational his work would become to all of thermodynamics, or if he was just trying to make better steam trains. Either way, he basically showed that waste is a feature, not a flaw. Every time your car engine runs, it converts fuel into motion, yes, but also into heat, noise, vibration, and a surprising amount of sweat if the AC is broken. Only a fraction of the fuel's energy actually moves the wheels, the rest goes poof. Entropy cashes in. Same with your phone. Its battery stores chemical potential energy, which gets used to power circuits, display TikToks, and light up your group chat at 2 a.m. But the phone also gets warm. That heat? Entropy's invoice. Even thinking produces entropy. Your brain, as sleek and mysterious as it is, operates by moving ions across membranes and firing synapses. It's incredibly energy hungry, burning about 20% of your body's total energy even though it's only about 2% of your weight. That's a lot of brain sweat. And guess what? Most of that energy ends up as heat. Because neurons aren't magic, they're meat-based machines running on entropy-heavy biochemistry. There's even a slightly unsettling idea in physics called Landauer's principle, which says that every time you erase a bit of information, like deleting a file or resetting a memory, you create a small amount of entropy. That means your digital spring cleaning isn't as tidy as it looks. Somewhere, in some microscopic way, the act of erasing adds to the universal mess. Let's pull back. Entropy is built into the very functioning of machines. You want cool air? You have to heat something else. You want motion? You need to burn fuel and release exhaust. You want to keep your leftovers fresh. The kitchen gets warmer. It's a cosmic trade-off system, and the house always wins. But here's where it gets cheeky. Some of our machines lie about their relationship with entropy. They appear sleek, silent, effortless. Think electric cars, smartphones, even those energy-efficient LED bulbs. But the entropy isn't gone. It's just hidden upstream. Take that electric car, for example. It doesn't belch exhaust like a gas guzzler. But the electricity that charges it, that often comes from power plants, some of them still running on coal, natural gas or nuclear fission. And those plants are spewing entropy like a fog machine at a school dance. Even renewable energy, solar, wind, hydro, creates some entropy during production, maintenance and transmission. Less than fossil fuels, yes, but the mess is still there, just more polite. Quirky tidbit of the night. There's a theoretical concept called a perpetual motion machine, a device that could operate forever without an external energy source. Physicists love to talk about them because they're completely, absolutely, 100% impossible, and yet people have been trying to build them for centuries. One design involved a wheel with weights that supposedly kept it spinning forever. Another used magnets arranged in a way that was supposed to create infinite movement. Spoiler alert, none of them work. Ever. The second law always ruins the party. The dream of free energy is so appealing, because we imagine we can outwit entropy. But there's no trick, no shortcut, no infinite spin. Everything we do costs something, especially order. So what's the takeaway here, as you lie in the dark, perhaps warmed by a fan, cooled by a vent, phone charging nearby? Just this. Every machine in your life is part of the great entropy game. They all take in usable energy and turn it into something slightly messier. You can delay disorder, redirect it, hide it, but you can't eliminate it. And that's okay, because what those machines give us, comfort, convenience, connection, is worth the cost. You get cool food, warm showers, lit rooms, endless cat videos, all for the price of a little ambient chaos. Entropy isn't sabotage, it's just the background fee for living in a universe that lets you do anything at all. So next time your fridge hums, your phone warms, or your car rumbles to life, remember, they're not breaking the rules, they're playing the game. And for now, so are you. You've probably lost a sock, no judgment. It happens to the best of us. You put 2 in. The machine hums, you open the door, 1 is gone, forever. Did the dryer eat it? Did it slip into another dimension? Is there a secret sock utopia we're not invited to? Or maybe, just maybe, this is entropy's most playful crime scene. But tonight we're not just blaming entropy for laundry crimes. We're going deeper, into the world of information theory. Because somewhere between disappearing socks and vanishing data, entropy plays a second role. Not just the spreader of disorder, but the mathematician of uncertainty. Let's dim the lights on the laundry and open up a different door, one into the mind of Claude Shannon. Back in the 1940s, Shannon, a soft-spoken genius working at Bell Labs, laid the foundation for digital communication. Phones, computers, Wi-Fi, texts, emojis, all of it traces back to his work. He was trying to solve a practical problem, how to send messages efficiently without losing meaning. And to do that, he borrowed a word from thermodynamics, entropy. Shannon's entropy is a measure of uncertainty in information. The more unpredictable a message is, the more entropy it has. For example, if someone sends you a message that just says, "ah," It has low information content, low entropy. But if the message is X7 at GZ3 ! That's way more unpredictable, high entropy. And why does this matter? Because in communication, reducing uncertainty is the name of the game. Every time you send a text, your phone compresses it, encodes it, transmits it, decodes it, and tries to deliver it without error. All of that is a battle against entropy, against noise, interference, misinterpretation. Just like your brain. When you talk, you choose your words carefully, most of the time. Your brain balances clarity with compression. You don't describe an apple as a round organic sugar sphere of red photosynthetic tissue, unless you're trying to lose friends. You say apple, efficient, familiar, low entropy. But the brain is a noisy place. Neurons misfire, memories fade, words get jumbled. Ever forget someone's name right after they tell you? That's information entropy. The signal-to-noise ratio dropped below usable. And don't even get started on dreams. High entropy nonsense, most of them. Here's where it gets spooky. Information entropy and thermodynamic entropy aren't just metaphorically related, they are mathematically linked. Both describe the number of possible states a system can be in. Whether it's a gas molecule in a box or a bit of data in a message, entropy tells us how much surprise, randomness, or chaos we're dealing with. So yes, your lost sock has entropy. And so does the last message you sent your ex. Let's look at your computer for a second. Just sitting there innocently glowing. Inside, it's flipping billions of binary digits every second, ones and zeros, arranged in patterns that form everything from cat videos to love letters. But the more compressed or encrypted that data is, the higher its entropy. It becomes harder to predict, which is great for security, but not so great if the system gets corrupted. That's where error correction comes in. Every streaming service, every online call, every satellite transmission relies on error correction codes, ways to detect and fix mistakes caused by entropy along the way. You don't notice it, but behind the scenes, little digital janitors are sweeping up dropped bits and fuzzy signals to keep your videos smooth. Quirky tidbit: NASA's Voyager spacecraft, launched in 1977, is still sending data back to Earth from the edge of the solar system. But those signals are incredibly faint, distorted by time and cosmic noise. Engineers use some of the most robust error correction methods ever devised to decode those whispers from deep space. Even in the vacuum, entropy tries to garble the message. Now let's bring it back to your room, your world. Every time you organize something, your files, your thoughts, your sock drawer, you're managing information entropy. You're reducing uncertainty, bringing clarity to chaos. But it never stays that way. Files get duplicated, folders fill with mystery items, notes lose context, socks vanish. Because information is fragile. It degrades, it mutates, it multiplies. The average human brain contains about 86 billion neurons, each connected to thousands of others, forming trillions of pathways. And yet, one sleepless night can make you forget where you parked your car. Entropy is not subtle. Historians still debate whether early information theorists like Shannon intended for their mathematical models to apply to human thought, but the overlap is impossible to ignore. Memory, learning, perception, they all follow the rules of systems seeking order amidst noise. Your brain is the most sophisticated noise filter in the known universe, and even it struggles. So what does all this mean? It means that the same principle causing heat to spread, stars to dim, and coffee to cool is also causing data to get corrupted, texts to misfire, and names to slip your mind. Entropy doesn't just tangle your physical world, it tangles your mental one too. And yet, here you are. You remember some things. You say what matters. You hold on to a few bright thoughts in the static. You organize your hard drive, even if just for a week. You find one matching sock and call it a win. Entropy always increases, but information is still possible, meaning still exists. And sometimes, improbably, your message does get through. So next time you lose something, an idea, a word, a sock, don't get frustrated. Just remember, you're not failing. You're just living in a universe that slowly scrambles everything. But not tonight. Tonight, you remember what matters. And maybe, just maybe, your other sock is right there, curled up at the end of the bed. You blink through the flicker of your screen, and for a moment you're looking not at science, but science fiction. A world ending in fire, a frozen city beneath a pale sun, a lonely astronaut staring at the stars as they fade into silence. Entropy isn't just haunting your physics class, it's moved into pop culture, quietly stealing the spotlight in everything from dystopian blockbusters to moody indie games. And half the time, you don't even realise it's there. Because entropy, it's the ultimate silent villain. Let's start with the big guns, heat-death endings. You've seen them. The slow fade. The universe growing cold and dim, stars flickering out one by one. Movies like Interstellar, Sunshine, or The Wandering Earth flirt with this cosmic quietus, where the end isn't explosive but inevitable. It's not a meteor or a supernova. It's just everything giving up. The sun expands, the planet burns, entropy wins, roll credits. Historians still debate whether early science fiction writers really understood thermodynamics or just borrowed the vibe. But by the mid-20th century, entropy had become shorthand for cosmic hopelessness. A subtle backdrop to stories about dying machines, ancient civilizations, and last messages from lonely satellites. In Isaac Asimov's famous short story, The Last Question, humanity asks a supercomputer how to reverse entropy. The computer keeps saying it doesn't have enough data. Over trillions of years, civilizations die, stars collapse, and the universe darkens. And finally, in the end, spoiler alert, it figures it out. But there's no one left to hear the answer. A quirky tidbit. Asimov considered that story his best work, not for the science, but for the feeling. That deep, aching tension between knowledge and futility. Because entropy isn't just about heat and molecules, it's about what can't be undone. And that's why storytellers love it. Take dystopias. You've seen them 1,000 times. Cities overrun, power grids failing, nature reclaiming the suburbs, society unravelling into tribal chaos, all dusty and dramatic. These aren't just moral tales, they're entropy manifest. Complex systems breaking down into simpler, messier parts. Law into anarchy, civilization into survival, Netflix original series into endless reboots. Even zombie movies at their core are entropy tales. Bodies no longer maintaining order. Societies failing to contain infection. Entropy with teeth. Let's talk about time travel. Sci-fi's favourite loophole. In a world ruled by entropy, time travel is the ultimate rebellion. What if you could go back? What if you could undo the spill, unmix the cream, reassemble the shattered glass? Shows like Dark, Doctor Who, or Tenet explore this temptation, the urge to reverse the irreversible. But entropy always waits. Even when you bend time backward, it resists. Remember, entropy isn't a technical glitch, it's a statistical truth. Even if you rewind the clock, the odds of perfectly restoring order are basically zero. And the more you try, the messier it gets. That's why time travel stories so often end in paradox, loss, or resignation. Because deep down we know, some things can't be undone. Not by machines, not by genius, not by love. Now look at Wall-E. Yes, the adorable trash robot. He's literally rolling around in a post-entropy wasteland, trying to create pockets of order, one crushed cube at a time. A robot fighting decay with routine, with care, with a tiny green plant. That's entropy resistance in Pixar form. Or Children of Men, where humans have become infertile. No new life, no future. The world slowly unspooling into chaos. That's not just a plot. It's a metaphor for entropy. The gradual end of potential. You can find entropy everywhere once you know how to look. The Matrix, simulated entropy in digital form. Mad Max, social entropy, dust-fueled. An AI that slowly turns on its creators? That's an informational entropy bomb with a Wi-Fi signal. Even Frozen 2, yes, Frozen 2, has a subplot about ancient balance breaking down and natural forces falling into disorder. Elsa may sing about letting it go, but nature remembers the second law. Why are we so obsessed with this idea? Because entropy taps into something primal. The fear that nothing lasts. That no matter how perfect the moment, the system, the society, it will decay, fade, break. And yet, stories always push back. Frodo destroys the ring, humanity reaches the stars, Wall-E finds life again. There's entropy, sure, but there's also effort, rebellion, hope. Even in the bleakest fictional endings, there's usually one light left on, one spark, one character who chooses to tidy something, fix something, or remember what once was. And you've been there. Ever rewatched a movie just to feel something again? That's your personal act of entropy resistance. You know the story, you know the ending, but you hit play anyway. Because repetition, familiarity, is how we keep order alive in a messy, shifting world. Just like rituals, bedtime routines, favourite books, old photos, all of them are little time machines of meaning. They can't reverse entropy, but they hold it at bay. For a while. You here now, tucked in and listening to a soft-voiced narrator talk about thermodynamic doom. You're participating in the same tradition, using story to make sense of chaos, to put a frame around the fading light, and that's beautiful. So let the stories continue, let the stars die in cinema, let the worlds crumble on screen. Because every time you feel something in the face of entropy, you prove it hasn't won yet. You still care, and that means order still matters. You're not in your room anymore, at least not fully. You're floating, digitally, mentally, metaphysically, inside a glowing grid, pulsing with artificial stars. Neon lines form a false horizon. Code runs beneath your feet. This isn't reality. Not exactly. It's simulation. Or is it? Somewhere, in a quiet lecture hall or an over-caffeinated late-night Reddit thread, someone's asking, what if the universe is a simulation? And more importantly, can entropy prove it? Let's begin with the weirdest part. This isn't a fringe idea anymore. Some very real physicists, philosophers, and tech billionaires have flirted with the notion that our reality is artificial, that we live inside a computer model run by beings we'll never meet, for purposes we'll never understand. Creepy? Yes, but maybe not so far-fetched. And entropy, it's at the centre of this virtual mystery. Let's rewind to what a simulation even means. In essence, it's a model, a simplified version of something real. A video game simulates gravity, a weather model simulates storms, a physics engine simulates collisions and explosions, and yes, your favourite ragdoll glitches. If you were designing a universe simulation, you'd want some rules to keep things consistent. That's where thermodynamics comes in. A perfect universe might feel boring, too orderly, too fake. But a universe that runs down, where stars fade, order breaks, and time only moves forward, that feels real. Entropy is what makes a simulation believable. It creates irreversibility, consequence, drama. You can't just reload the save. Every action changes something. Every bit of order you build burns fuel elsewhere. Historians still argue whether this entire concept, simulation theory, is just philosophy with cooler branding. But it gained serious attention in the early 2000s, when philosopher Nick Bostrom proposed a now-famous idea. If advanced civilizations can simulate universes, and they run many simulations, then statistically, we're probably in one. And if we are, then entropy might be the system's way of balancing the cosmic budget. Here's the digital twist. Simulations need to manage information. The more complex a world is, the more data it takes to render. If you've ever played an open-world game, you know how this works. The whole world doesn't render at once. Only what you see is processed. The rest exists in low-res or placeholder code until you get closer. So imagine a universe like that, running in the background, with entropy acting as a compression algorithm. It lets the simulation focus on complexity in the short term, while slowly degrading everything else to free up space. Order is expensive, so the system lets it unravel, slowly, elegantly. Every sun that dies, one less high-resolution fireball to simulate. Every black hole that evaporates, a tidy memory flush. Every galaxy that slips beyond the cosmic horizon. A corner of the screen fading to black. In this view, entropy isn't a cosmic accident, it's a design feature. Now for a quirky tidbit. In some advanced simulations, developers use something called procedural generation, letting algorithms create content on the fly rather than manually coding every detail. Think Minecraft worlds, or those endless auto-generated galaxies in No Man's Sky. It's efficient, elegant, entropic even. Our universe shows suspiciously similar behaviour. Quantum randomness, fractal patterns, scale invariance. Some physicists have noticed the math of reality feels computable, as if it's being generated as needed rather than stored in full. One researcher even suggested that if you look closely enough at the fabric of space-time, you might find pixelation, a smallest unit, like a Planck-length bit. If the universe is digital, entropy could be how that digital system keeps itself from overheating, literally and figuratively. But let's not get too lost in the matrix. Whether or not we're in a simulation, entropy still behaves the same. It still increases. It still defines time. It still puts an expiration date on everything. And that exploration? It gives weight to our choices. In a world without entropy, nothing would change. No decay, no aging, no progress. A universe without entropy would be like a paused game. Perfect, but frozen. Unplayable. So maybe entropy isn't the glitch in the simulation. Maybe it's the reason the simulation runs at all. You right now, lying quietly in your room, are made of atoms that obey this simulated, or not so simulated, rulebook. Your body is full of processes, heating, decaying, moving toward entropy. But you're also full of memory, and intention, and a strange, beautiful desire to resist the slide. You make lists, you clean rooms, you tell stories, you fall in love. All of these things are temporary structures, little sanctuaries of meaning against the tide. And if we are in a simulation, well, you're still real. Your thoughts are still happening. Your experience still matters. The pixels may be virtual, the code may be borrowed, but the entropy is real enough. It's your reminder that time is limited, memory is precious, and nothing good lasts forever. So maybe stop scrolling and call your mom. So tonight, close your eyes if you haven't already. Let the world pixelate around you. Whether it's a simulation or not, you've made it this far. You've kept your corner tidy, you've played the game well. And entropy, it can wait until morning. You're drifting again. This time not through the stars or a simulation, but into the tiny twitching quantum fuzz of reality. Here, nothing is smooth, nothing is certain. The laws of big things, planets, engines, ice cream melting on the counter, take a back seat to the jittery rules of the very, very small. Welcome to the quantum world, where entropy still rules, but not without a fight. You might think that thermodynamics and quantum physics are from two different planets. One deals with steam engines and burning toast, the other with teleporting particles and cats that are somehow both alive and not. But these two worlds are deeply, bizarrely connected, especially when it comes to entropy. Let's start with the basics. At the macro level, your room, your blanket, your cereal, entropy behaves predictably. Systems move from order to disorder, coffee cools, socks vanish, no surprises there. But down at the quantum level, things get squirmy. Particles don't have fixed positions or velocities. Instead, they exist in probability clouds, blurry maybes until you observe them. This is the infamous Heisenberg uncertainty principle. And in this landscape of maybes and maybe-nots, defining order and disorder becomes complicated. Here's the kicker. Quantum systems can be in superposition, where they exist in multiple states at once, and they can become entangled, meaning the state of one particle instantly affects another, even if they're light years apart. Einstein called this spooky action at a distance, which, let's be honest, sounds like a rejected dating app feature. So what does this mean for entropy? Well, here's the strange part. Quantum systems can appear to violate the second law of thermodynamics. Briefly, tiny particles in isolated systems can experience temporary decreases in entropy. It's called a fluctuation. Imagine a microscopic unmelting of ice, or a spontaneous regrouping of mixed cream into coffee. It sounds impossible, but at scales that small, randomness can briefly go the other way. But, and here's where entropy reclaims its crown, these moments are fleeting, rare, and utterly dwarfed by the larger trend. On average, over time, entropy still increases. The universe keeps moving forward. No loophole here, just a quantum stutter in the music. Historians still argue whether these tiny reversals are just mathematical quirks or clues to something deeper. Some suggest that understanding entropy at the quantum level might unlock new physics, maybe even quantum gravity or a theory of everything. One of the most fascinating areas of this research is quantum information theory, which tries to blend Shannon's digital entropy with quantum weirdness. In this world, information is physical. It takes space, it affects energy. And when quantum information is erased, just like classical information, entropy rises. Even stranger, there's mounting evidence that entanglement entropy, a measure of how tangled up particles are, might be the true building block of spacetime itself. Some physicists think that the geometry of the universe emerges from patterns of entanglement. Let that sink in. Not atoms, not strings, not matter or energy. But entropic relationships between quantum bits might be what creates space. In this view, the fabric of reality is woven not from stuff, but from uncertainty. Order and disorder aren't just side effects, they're ingredients. Quirky tidbit time. One experiment showed that when you erase switch path information from a quantum system, You can restore interference, essentially undoing entropy's effect on the outcome. It's as if you tell the universe, "Shh, forget I looked," and it obliges. But you have to be subtle. The quantum world is sensitive. Once you measure, observe, or interact, the wave function collapses and the options narrow. Entropy steps in, like a librarian telling you the reading room is closed. Still, this delicate dance suggests something profound. Entropy is deeply tied to what we know and what we choose to observe. It's not just physical, it's informational. It's what you could know, but don't. This brings us back to the quantum arrow of time, a hotly debated idea. At the quantum level, most equations are time-symmetric. They work the same whether time runs forward or backward. But we don't experience time that way. And the reason, once again, seems to come back to entropy. When a quantum system interacts with a large environment, say you checking the time on your phone, it undergoes decoherence. The superpositions vanish, the probabilities collapse, and entropy jumps, irreversibly. That's your arrow of time right there. The moment order became memory and possibility became fact. Once that happens, no going back. And that's why even quantum weirdness can't rescue us from the second law. Entropy may wobble, but it doesn't fall. So here you are, caught between scales. Your body obeys classical thermodynamics, heat flows, energy depletes. But your atoms, your electrons, they're playing a quantum game you'll never fully see. You are a macro-organism powered by quantum mysteries, slowly unraveling in a sea of probability. You are a warm tangle of certainty and chance, and somehow, against all odds, you stay coherent. At least for now, so curl deeper into your blanket. Let the world shrink down to molecules. Let time wobble. Let entropy do its thing. Because even when it plays dice at the smallest scales, the universe still rolls towards sleep. The wind scrapes softly across a barren landscape, crimson dust curling into the thin sky. Somewhere in the distance, a mechanical rover creaks along, its camera swiveling like a sleepy periscope. It pauses, takes a photo, sends it home, a silent witness to a world ruled entirely by entropy. Welcome to Mars, where even the rocks look tired. And not just Mars. All across the solar system and far beyond, entropy is writing the same slow, irreversible script. No matter the atmosphere, or lack of one. No matter the temperature, gravity, or age. Every planet, moon, comet, and asteroid is falling towards stillness. So tonight let's wander. First stop, Venus. You'd think, with its thick atmosphere and perpetual cloud cover, that Venus might be lively. But step a little closer, and you'll see the truth. Venus is entropy's pressure cooker. Temperatures hit nearly 900 degrees Fahrenheit, hot enough to melt lead. The surface is crushed under an atmosphere 90 times denser than Earth's. It's a place where entropy isn't just increasing, it's fully leaning in. Once, scientists speculated Venus might have been Earth-like, perhaps even watery. But at some point, a runaway greenhouse effect took over. Gases trapped heat. Water evaporated. Carbon dioxide flooded the skies. The planet became a planetary sauna that never shuts off. Now it simmers, lifeless, melting, a tomb of possibility. Then there's Mars, Earth's quieter cousin. Once upon a time it had rivers, lakes, maybe even oceans. But over billions of years its atmosphere thinned, its magnetic field fizzled, and its surface dried out. What remains is an ancient memory of movement, now frozen in place. You can see it in the channels, the deltas, the rocks that were once rolled by water. Mars is a planet caught mid-transformation, frozen just before entropy finished the job. There's no weather to clean up the dust, no tectonics to recycle the crust. Mars is stuck, inching toward equilibrium with every grain of sand carried by the wind. Historians still argue whether the Mars rovers, Curiosity, Perseverance, and the rest will be our greatest monuments or our loneliest. Machines resisting planetary entropy for as long as their batteries hold. Now turn your eyes to Europa, one of Jupiter's moons. On the surface, a hard, icy shell, crisscrossed with dark, chaotic fractures. But beneath that ice, a liquid ocean, possibly warm, salty, and full of potential. Tidal forces from Jupiter create friction inside Europa's core, keeping it warm. It's a local victory against entropy, one that might be hiding life. That's the funny thing. Sometimes entropy gives life a little window. Tidal heating, radioactive decay, sunlight. tiny bursts of usable energy in a sea of cold. They don't stop entropy, of course, but they let life take root for a while, they delay the inevitable. And then there's Titan, Saturn's smoggy orange moon. It has lakes, not of water, but of liquid methane and ethane. Its atmosphere is thick with hydrocarbons. It rains gasoline, basically. It's wild, it's dark, it's deeply entropic. But oddly enough, Titan's complexity makes it low in entropy compared to the gas giants that surround it. There are processes happening, weather, flow, cycles, for now. Because out there, far from the sun, everything slows down, solar energy fades, molecular motion drops, entropy still rises, but it crawls. The further you go, the colder it gets, the longer things last, but they're also more frozen. Change becomes rare. Chaos becomes calcified. There's no fire to burn through fuel, no sunlight to stir the pot, just slow fading. Take Pluto. Once a planet, always a frozen rock. Its surface is ice and nitrogen snow, with occasional hints of activity, glaciers slowly shifting, gases sublimating into the void. But even those tiny processes are entropy at work. Pluto is leaking heat, ever so gently into the nothingness beyond. And beyond Pluto, the Kuiper Belt, the Oort cloud, a thin, scattered smear of icy leftovers, orbiting far from the sun's warmth. These objects are quiet, dormant, waiting to be nudged, waiting to fall, or not. In deep space, entropy doesn't need to rush. It has time, billions of years, eons even, to grind everything down. Here's a fringe tidbit. Some scientists believe that life could one day survive on rogue planets, worlds that have been flung from their solar systems, drifting through interstellar space. If they had enough geothermal heat, or thick enough atmospheres, or were just lucky enough to host energy-storing chemistry, they might harbour microbes even as they drift in eternal night. But even there, entropy rules. No system is safe, no planet is sacred. Everything winds down, every hot core cools, every battery dies, and yet, here you are, warm, conscious, hearing these words on a tiny blue planet that's not done yet. Earth is still fighting entropy with every thunderstorm, every tectonic rumble, every blade of grass photosynthesizing its way through a Tuesday afternoon. We are for now a world full of processes, cycling energy, fighting decay, spending light like it grows on trees. And maybe you wonder, is that the point? Are we the universe's way of using up its own potential before it slips away? Possibly. But there's meaning in that. Because every world you just visited, from Venus's furnace to Europa's buried ocean, is a chapter in the entropy story. A different flavour of fading, a different tempo to the same unwinding song. So as you close your eyes, picture yourself orbiting slowly above it all. Planets turning, moons glowing, everything, everywhere moving towards stillness, but not there yet. You've still got time, you wake up, stretch, yawn, and somewhere deep in your cells something ancient stirs. Not the coffee craving, that's newer. No, this is older than tools, older than fire, older than language. It's the quiet instinct to survive, to grow, to adapt, to outpace entropy for just a little while longer. This is the story of evolution, and how life itself is a strange, brilliant rebellion against the second law of thermodynamics. At first glance, it seems like life breaks the rules. Entropy says systems move from order to disorder, right? But life takes chaos, random molecules, sunlight, water, and turns them into cells, tissues, brains, TikTok dance trends, all incredibly structured, all weirdly organised. But, and this is the key, life doesn't cheat entropy. It pays for its order with every breath, every bite, every exhale. Let's start at the beginning. Around 4 billion years ago, Earth was a mess. Volcanoes, lightning, toxic oceans, nothing that looked even remotely cozy. But in that chaotic soup of molecules, certain chemicals began to self-organise. Lipids formed membranes. Proteins started folding. Nucleic acids began storing information. And eventually, miraculously, mathematically, entropically, life emerged. Historians, well, biologists, still argue over how this happened. Theories range from deep-sea hydrothermal vents to alien comet delivery systems. But the thread running through all of them is energy flow. Life didn't start in still water. It started where energy moved, from hot to cold, from high to low, from sun to sea. That energy flow allowed systems to grow in complexity, not by violating entropy but by using it. Here's how it works. Entropy must increase in a closed system, but Earth isn't closed. It gets a constant influx of low entropy energy from the sun. Plants absorb this light and use it to build sugar molecules, concentrated little packages of order. Then animals eat the plants, other animals eat those animals, and so on. Each step in the food chain passes on a little less energy, a little more disorder. But the local system, your body, your brain, your pet lizard, can maintain low entropy by constantly burning fuel. You're basically a walking campfire that rearranges molecules, and over time these biological systems evolved. They got better at extracting energy, more efficient at storing information, better at resisting entropy, however temporarily. Natural selection, in a way, is just the universe rewarding structures that can sustain low entropy long enough to reproduce. If you're good at surviving, at holding your shape, you get to make more copies of yourself. If not, the tide takes you. Here's a weird tidbit for your pillow thoughts. DNA is one of the most efficient information storage systems in the known universe. It can encode huge amounts of data in an astonishingly small space. Scientists have even started storing digital files in synthetic DNA, because entropy is less aggressive there, at least for a few thousand years. But back to evolution. Over billions of years, life has grown more complex. Cells to tissues to organs to nervous systems to conscious minds. This complexity might look like a defeat for entropy, but it's not. It's just entropy redistribution. Every new level of organization burns more energy. A brain uses far more calories than a single-cell amoeba. A human city generates vastly more entropy than a beehive. We build bigger structures, but the price is bigger messes. Take the human body. It runs beautifully usually, but it's a delicate system. Temperature, pH, electrolytes, oxygen, all tightly regulated. Homeostasis is just another word for barely holding off entropy. And when it fails, systems break, order collapses, cells die, entropy wins again. Even our social evolution reflects this. Societies organize to protect individuals from disorder, governments, schools, garbage collection. But as we saw before, those systems generate their own entropy. The more order we create, the more energy we burn, the more mess we shift downstream. It's turtles all the way down, and they're all slightly exhausted. Let's zoom out again. Earth, from space, glows in infrared. That's entropy escaping, heat radiating into the void. We take in high-energy sunlight and return it as low-energy heat. The entropy exchange is constant, graceful, and totally unavoidable. Even our evolution toward intelligence, toward complex thought, is just entropy playing 4D chess. Consciousness lets us predict threats, plan ahead, save energy, store information. But it also lets us feel things like regret, nostalgia, and an eerie understanding that all things fall apart. You're not alone in that realization. Even Darwin felt it. He once wrote that contemplating the origins of life made him feel cold all over. That wasn't just a chill, it was entropy, whispering politely. But here's the beauty. Even though we're doomed to dissolve eventually, evolution gave us the tools to notice it, to marvel at it, to record it in poems and lab notes and bedtime science scripts. That's kind of incredible, because entropy doesn't get to erase meaning. Not immediately, not if we pass it on. So tonight, as you lie still, remember that your body is the result of billions of years of careful entropy management. Every muscle, every neuron, every heartbeat is part of a lineage that figured out how to delay the fall long enough to make more life, long enough to make memories. You're entropy's finest accidental creation, and somehow, you're still here. Somewhere, in the background of everything the universe is tidying up. Not in the neat, satisfying sense, not with labelled bins and colour-coded folders. No, this is entropy's version of tidying, dismantling, flattening, recycling everything into stillness. And as it turns out, the universe may have options for how it ends, because while we've spent all this time talking about the heat death, that's just one ending, one version of the curtain fall. There are others, some slow, some violent, some so strange they feel like fiction, but they all share one thing. Entropy has the final say. Let's take a little stroll through the possibilities. First up, the headliner you've met already, the heat death of the universe. This is the long, lonely fade, the the slow drift toward maximum entropy. Stars die, galaxies dim, black holes evaporate, and everything ends up the same temperature. Uniform, unchanging. A cosmos full of particles with nowhere to go and nothing to do. No bang and no crash, just quiet. But some physicists argue this may not be the only fate. So we turn the page and there it is, the big crunch. In this version, gravity decides to pull rank. After billions or trillions of years of cosmic expansion, gravity slows everything down and then reverses it. Galaxies begin to contract. The universe shrinks. Heat increases as everything packs tighter and tighter. Eventually it all collapses into a single point, like the reverse of the Big Bang. A cosmic in-breath. And what do you get when the universe collapses to a point? Possibly a restart. This brings us to a more whimsical theory, the Big Bounce. Imagine the universe as a yo-yo on a very long string. It expands, reaches a point of maximum stretch, and then recoils, crashing back down, only to bounce again. A cycle of birth, death, and rebirth. Each bounce wipes the slate clean. But there's a catch: entropy. If entropy increases with every cycle, each universe would be messier than the last. Eventually the system would max out. No more bounce, just one final collapse into a sticky high entropy splat. Historians still argue whether ancient cosmological models, like those from Hindu or Buddhist traditions, anticipated these cycles in poetic form. It's hard not to see echoes. Now for something newer and much scarier. The Big Rip. Here, dark energy takes center stage. You've heard of it. It's the mysterious force driving the universe's accelerating expansion. Right now, it's just stretching galaxies apart. But what if its power increases? If that happens, the expansion could speed up exponentially. Galaxies wouldn't just drift, they'd rocket away from each other. Stars would be torn from galaxies, planets from stars. Eventually, even atoms would be pulled apart. Space-time itself would tear. Everything ends in a flash of disassembly. No time for goodbyes. That's entropy gone wild. Instead of creeping toward uniformity, the universe violently explodes into disconnection. Every structure, from solar systems to quarks, gets shredded by expansion. There's also the vacuum decay scenario. You're really going to sleep after this one, I promise. This theory suggests our universe is in a false vacuum, a temporary unstable energy state. If a more stable state exists, a tiny bubble of it could suddenly appear, expand at near light speed, and rewrite the laws of physics as it passes through everything. It's like hitting a cosmic reset button, with no warning, no survivors, and no one left to care. But wait, you say, isn't this just theoretical doom scrolling? Maybe, but there's a hopeful twist. Even in these apocalyptic scenarios, entropy has a purpose. It's not just destruction, it's transition. It's the system exhausting its current options, making way for new configurations. The Big Bounce needs entropy to clear the board. Vacuum decay needs energy gradients to move forward. The heat death. It might be the universe's final save state, waiting for an as-yet undiscovered process to stir it back to life. And some theorists whisper, very softly, that entropy might reset itself. How? Enter the realm of speculative physics. Some suggest that quantum fluctuations in a high-entropy universe could, over ridiculous timescales, spontaneously create new, low-entropy pockets, tiny baby universes, each one with its own Big Bang, its own rules, its own arrow of time, maybe even its own you. Quirky tidbit. There's an idea called the Boltzmann brain, a hypothetical, self-aware brain that spontaneously forms out of chaos in a high-entropy universe. It would briefly exist, full of false memories before dissolving. Some physicists hate this idea. Others think it's a natural consequence of entropy gone too far. But let's not end on a rogue brain. Let's remember this. Even in every possible ending, entropy is the storyteller. It sets the pacing. It decides when systems can evolve, when stars can burn, when life can emerge, and eventually when it's time to recycle the set. Because the universe is a recycling program. Every atom in your body has been part of a star. Every breath you take contains molecules exhaled by trees, dinosaurs, and possibly Queen Elizabeth I. Entropy takes what was ordered, mixes it, scatters it, and builds again. Differently, slowly, inevitably. You are right now part of that transformation. Not outside it, not fighting it. Part of it. a temporary configuration of atoms and energy, playing your little part in the grand thermodynamic play. And when your time comes, when your heat spreads and your structure loosens, you'll return to the pool, your pieces will be reused, entropy will fold you into the next thing, and the story will continue. You've heard it over and over like a cosmic mantra. Entropy always increases. The arrow of time flies in one direction. Things fall apart, order crumbles, but you're wondering, maybe quietly, maybe with a whisper of rebellion in your pillow-warmed thoughts, can entropy ever be reversed? Can we, in some hidden way, roll the universe back up? Tonight, we chase that impossible dream, and we start with the strange, the bold, the speculative, because that's where all the good physics hides. First up, time-reversed universes. There's a legitimate idea in theoretical physics that the universe might not just be expanding in one temporal direction. Some models suggest that, at the moment of the Big Bang, not only did our universe explode outward into space, but also that another universe exploded backward in time, a mirror universe, one where entropy increases in the opposite direction, where people unage, uneat, and maybe even unlisten to this script. Quirky? Yes. But it's not science fiction. This idea comes from actual work in cosmology and time symmetry. Some physicists think it could explain why the universe started in such a low entropy state in the first place, by balancing itself across the time axis like a seesaw. Historians still argue whether these mirrored time ideas hold up under observation, or if they're just mathematically convenient ways to avoid that awkward question. Why was the universe so ordered to begin with? Now let's visit a weirder place, the land of Boltzmann brains. You met them briefly last time, those hypothetical disembodied minds that could spontaneously pop into existence in a high-entropy universe. Because if you wait long enough, and the universe keeps fluctuating at the quantum level, eventually some random arrangement of particles will resemble a brain, complete with thoughts, memories, dreams of a life it never lived. That's entropy in reverse. For a flickering moment, disorder organizes itself by pure chance into something structured. But here's the twist. The odds of creating a single Boltzmann brain are higher than creating an entire structured universe like ours. So some physicists nervously ask, are we just Boltzmann brains? Are we the unlikely product of chaos thinking we're real? Don't panic. That theory has been largely set aside as problematic and, frankly, kind of rude. But it highlights a deeper truth. Reversing entropy is not impossible. It's just so statistically unlikely that it might as well be. But what about locally reversing entropy? You do it all the time, actually. Every time you clean your room, organize your thoughts, eat a salad and convert it into muscle and warmth and awkward conversation at brunch. You're reducing entropy in yourself by increasing it somewhere else. A fridge, as we've seen, lowers entropy inside but increases it overall. A living cell maintains order by taking in energy and spitting out heat and waste. Even Earth does it. It absorbs the sun's organized photons and re-emits messy infrared radiation. The math checks out. The universe is still increasing in entropy overall. But you're surfing the wave for a bit. Now for the boldest question. Could advanced civilizations ever reverse entropy? Let's say you have an unlimited supply of energy. Could you run some fantastically clever machine that reorganizes the universe, molecule by molecule? Could you unmix the cream, unburn the toast, unkill the star? Some have speculated about Maxwell's Demon 2.0, not a thought experiment this time, but a futuristic AI or hyperintelligence capable of managing trillions of particles, keeping them all in line like a cosmic traffic cop. But there's a catch. There's always a catch. As we learned before, managing information costs energy. The more you measure, record, store, and delete, the more entropy you generate. So even a perfect entropy-fighting machine would have to dump even more entropy into its surroundings, and eventually it hits a wall. The ultimate limit is Landauer's principle, which says that erasing one bit of information adds a tiny, but very real, amount of entropy. Multiply that by a universe's worth of data. You've just made things worse, not better. Still, the idea persists. Some dreamers propose that maybe, at the end of time, the last intelligent beings, AI or otherwise, will use the dying light of the final stars to build a computer that simulates all past realities, restoring structure through computation rather than physical matter. This is called the Omega Point, a concept from mathematical physicist Frank Tipler, who believed the universe's collapse could allow infinite processing power in a shrinking space. As entropy increased, intelligence would rise faster, outrunning the chaos until, in the final moment, all knowledge is restored. It's not a widely accepted theory, but it's poetic. Because at its core, the idea that entropy could be reversed taps into something human, the refusal to accept endings, the belief that memory or love or beauty might somehow outlast decay, that maybe, just maybe, we can write the code that unravels the mess. But entropy is patient. It doesn't hate you, it doesn't want to end you, it just doesn't care. It's not an enemy. It's the background process that makes time real, that gives meaning to effort, that makes things precious. You don't need to reverse entropy to matter. Your life is meaningful because it's temporary. Your memories are sweet because they fade. Your warmth is comforting because it will cool. And yet, still, you try. You fix the thing. You clean the room. You write the song. You send the message. Every act of creation is a soft refusal, not to defeat entropy, but to dance with it. So no, you can't reverse entropy, not completely, but you can, for a while, make something beautiful before the tide carries it away. And maybe that's enough. The stars are gone. Not in a dramatic blink, not all at once, but faded, like candles burning down across a banquet table no one remembers setting. One by one, over billions of years, they've exhausted their fuel, collapsed inward, flared out, and finally settled. The light is over, the heat is gone, entropy has won. You float now in the far, far future, long after galaxies stopped forming, long after the last supernova flickered out in silence. The universe is a graveyard of embers, shadows, and slowly vanishing echoes. This is the slow fade to black, and it's not sad, it just is. The last white dwarfs have dimmed into black dwarfs, cold, inert spheres the size of Earth, but with the mass of the sun. They don't shine, they don't warm, they just sit, silently radiating whatever scraps of energy remain into the void. Even the black holes, the great cosmic hoarders, have done their time. They've leaked their hawking radiation into the darkness. One atom at a time, one photon at a time, they've given up their secrets. And now, they too are gone. What remains? A thin mist of particles, cold, lonely, spread across a universe so vast the distances between them are beyond meaning. No planets, no light, no boundaries, just subatomic stragglers, wandering through a field of nothing. No gradients, no pressure, no contrast. Maximum entropy. Everything is the same, and in that sameness, nothing can happen. Historians don't exist anymore, not in any traditional sense, but if they did, they'd tell you there was once debate about how long this would take. Some said 100 billion years, others said more. But in a universe where time has lost all urgency, numbers hardly matter. And yet, even here, at the edge of nothing, the story isn't quite over. There's a whisper of motion, a quantum flicker, an occasional dance of virtual particles popping into and out of existence. These fluctuations don't change the overall entropy. They're like foam on a frozen sea, but they hint at something profound. The universe is never truly still, not even at the end. A quirky tidbit for your final starry thoughts. In a universe at maximum entropy, probability becomes everything. Over vast enough timescales, truly absurd timescales, anything that can happen might happen. A new fluctuation, a spontaneous low-entropy pocket, a new universe. In this strange final act, entropy becomes the seedbed for future beginnings. Not because it desires rebirth, it doesn't desire anything, but because order can arise from chaos, if you wait long enough. Even in silence, potential lingers. You, of course, are long gone. Everyone is. But the atoms that made you, the heat, the motion, the memory, have been distributed across the stars, the void, the time between time. You were never really separate, just a pattern, briefly held together by borrowed energy. Entropy took you apart, yes, but it also allowed you. It made time possible. It made warmth possible. It made love possible. Without entropy, nothing would change. No coffee would cool, no song would end, no life would evolve. A static universe might be tidy, but it would also be meaningless. We don't live in that universe. We live in one where things fall apart, and because of that, things also come together, just for a moment. So now, as the final particles drift, and the background radiation spreads itself into irrelevance, the universe does what it has always done. It continues. Not with drama, not with despair, just with the patient certainty of physics. No more stars to burn, No more light to lose, no more stories to tell, but also no more tension. No more struggle, no more need. This is not the end. It's not even an end. It's a completion, a great cosmic exhale. So breathe out with it, one last time. Let the stillness wrap around you. Let the heat you once carried, the thoughts you once had, the atoms you once borrowed, return to the field. You were here, you made ripples, and then, like everything else, you became part of the still. The lights are out, sleep well, and now there's nothing left to explain. No more particles to chase, no more stars to count. Just you, wrapped in quiet, surrounded by the steady hush of your own breathing. Somewhere in the background the universe still hums, but it's softer now, like a lullaby that's almost finished. Entropy has carried us through everything tonight, from the swirl of cream in your morning coffee, to the slow death of galaxies, to the faint flicker of quantum ghosts in the void. And through it all you listened. You stayed with it. You didn't rush. You let the story unfold second by second, just like time itself. Maybe some of it slipped past you, blurred into dream. That's okay. Entropy's favourite trick is scattering things, and sometimes the pieces we forget are the ones we needed to let go of. There's peace in not remembering every word. There's beauty in letting the edges go soft. So wherever you are, whatever your sky looks like, whatever hour this is for you, know that you've wandered far tonight, across thermodynamic laws and time's arrow, across stars and thought experiments, and the sleepy tick of heat loss. And now there is only rest. Let entropy have the rest of the world for a while. Your corner is still, your bed is warm, and everything just for now is enough. You don't need to understand the universe tonight. You just need to drift within it. Held, weightless, quiet, sleep.